Welcome to Spring LIB.
In this exercise, we're going to be talking about both radius of curvature and circular motion, so I'm going to briefly review them. First, for radius of curvature, we have that if we have a general curve, an arbitrary curve like this one, and we want to calculate what is the radius of curvature of this curve at a certain point, x0, so we have y as a function of x, then the radius of curvature is equal to 1 plus the derivative of y with respect to x squared to the 3 halves divided by the magnitude of d2y dx2, and this should be calculated at x0. Now, regarding circular motion, we need to know that if we have a particle that's undergoing circular motion with a radius of r, then the acceleration of this particle can be decomposed into two components. One of them is the centripetal component that points towards the center, and the other one is a tangential component that is tangential to the trajectory. The centripetal component is equal to v squared over r, where v is the speed of the particle, r is the radius of the trajectory, and accounts for the change in direction of the velocity. The tangential component, on the other hand, is equal to dv dt and accounts for the change in speed. So now we can go to the exercise. So basically we have a box that has a mass m and an initial speed of v0, and the box is constrained to move in this parabola here. Y equals minus 0.5x squared. So our goal is to find first what is the speed v of the box as a function of x, and then we have to find what is the normal force that the parabola, the surface of the parabola, exerts on the box, and also the tangential acceleration. Okay, so what I'm going to do is, first of all, I'm going to draw the free body diagram on the box. So here we have the box, and here we have the parabola. Okay, notice that the forces that act on the parabola are the gravitational force that acts downwards and the normal force that acts perpendicularly to the surface. Okay, and what I'm going to do is to decompose these forces into two components. One of them that is perpendicular to the surface of the parabola, and the other one is tangential to the surface. Notice that the normal force is already perpendicular, so what we need to do is to decompose the gravitational force. Okay. Now notice that if we have this parabola here and we have a certain point, this one, then this angle here, okay, so this angle is theta, and we have that the tangent of theta is equal to minus the derivative of y with respect to x. And the minus is here because actually the derivative of y with respect to x is equal to this angle, the complementary angle, phi, and in order to find the tangent of theta, we need the minus sign. Okay, so this angle here, this means that this angle here is theta. Okay, and if we want to decompose into the r and theta components, we have that for the r component, we have the normal force. Actually, let me write the other way around. We have mg times the cosine of theta. And actually, I'm sorry, there's something wrong here in the picture. The angle that the angle theta shouldn't be this angle, it should be the opposite angle. I'm sorry for that. So it should be at this angle here. Now everything is correct. Now we can, in the r direction, we can find mg times cosine of theta minus the normal force is equal to m times the centripetal acceleration, that's v squared over r. And theta, in the theta direction, we have mg times sine of theta is equal to m times the tangential acceleration, at. Okay, so now notice that we don't know a couple of things here. We don't know what r is, and we don't know what theta is, so we can find what sine of theta and cosine of theta are. So we have to find these things. So first, I'm gonna go back to this formula here and find the tangent of theta. And then with the tangent, we can find both the cosine and the sine. So remember that y is equal to minus 0.5 x squared. So this means that the y dx is minus x. So the tangent of theta is x. Okay, so what I'm going to do is to use the formulas that the cosine of theta is equal to 1 over the square root of 1 plus tangent squared of theta, while the sine of theta is equal to 1 over the square root of 1 plus 1 over tangent squared of theta. Okay, so using that tangent of theta is x, we have the cosine is 1 over the square root of 1 plus x squared, while the sine of theta is x divided by the square root of 1 plus x squared. Okay, so now I'm gonna just rewrite these equations using what I just found. So we have the mg times 1 over the square root of 1 plus x squared minus the normal is equal to mv squared over the radius. And mg x divided by the square root of 1 plus x squared is equal to m at. So I'm going to use this second equation here in order to find the speed as a function of x. Okay, so first I'm going to find the speed. So we have mgx divided by the square root of 1 plus x squared. This is equal to mat. So I'm just going to cancel the m's, and we have that at is equal to gx divided by the square root of 1 plus x squared. Now remember that the tangential acceleration, as I said before, is equal to dv dt. And this is equal to gx divided by the square root of 1 plus x squared. Now I'm going to multiply both sides by v, so we have v times dv dt is equal to v gx divided by the square root of 1 plus x squared. Now remember that v is equal to ds dt. And I'm just going to explain what s is in a second. So we have ds dt gx divided by the square root of 1 plus x squared. Now consider that we have an arbitrary curve in our case. So let me write our specific curve. We have this curve here. And we have a coordinate system, yx. And dx is the element of length of this curve. Okay, so a little element of length here. Notice that ds is equal to the square root of dy squared plus dx squared. And I'm gonna write it a little differently as dx times the square root of 1 plus dy squared divided by dx squared. Notice that I just isolated dx in the formula, and using now that dy dx is equal to, up here, it's equal to, I'm sorry, where did I write it? So sorry for that. I wrote it here. I used that dy dx is equal to minus x. So dy dx squared is equal to x squared. And actually here, I forgot to use the parentheses. So now with the parentheses, I think everything looks tidier. So I have that ds is equal to dx times 1 plus x squared. Okay. So the dt's cancel out. So I have v dv is equal to ds, which, as I said, is dx times the square root of 1 plus x squared, gx divided by the square root of 1 plus x squared. So the square roots cancel out. We have that v dv is equal to xg dx, and I'm going to integrate from in both sides from x equals 0 to a certain value of x. When x equals 0, v is v0, and I want to find the value of v. So we have that v squared minus v0 squared divided by 2 is equal to gx squared divided by 2. So in the end, v is equal to the square root of v0 squared plus gx squared. This is the value of the speed as a function of x. That's the first thing we need to find. And we need to find also the acceleration, the tangential acceleration. That actually we've already found. It's this one here. So I'm just going to copy it. So we have the tangential acceleration is gx divided by the square root of 1 plus x squared. And then we have to find the normal force, and I'm going to use the equation for the r-coordinate in order to find the normal force. Notice that in the equation for the r-coordinate, if we isolate the n variable, we have that n is equal to m g cosine theta, and actually I already found out that cosine of theta is 1 over the square root of 1 plus x squared, minus m v squared, which according to point 1 here is the square is v0 squared plus gx squared divided by r. So now all we need to do is to find what r is. So remember that r is equal to 1 plus the derivative of y with respect to x squared. So that's 1 plus x squared. Okay, to the 3/2 divided by the magnitude of the second derivative of y with respect to x, which is just 1. So r is 1 plus x squared to the 3/2, which means that n is equal to m divided by the square root of 1 plus x squared times g minus v squared plus gx squared divided by 1 plus x squared. Okay, and this concludes our exercise.